in my house.
Yeah.
So like, no matter what you
Yeah.
get, one of the things you have to actually get it into your living. You get it in the university. I tell you,
How much is it? Is it like $7,000?
All right, here, folks. We're gonna start with we're gonna start here with a check for understanding based on this most recent lesson. These are just like, this is all in the OneNote. So like, and the answers are all in the OneNote, so you don't feel like you need to write anything down. We're just gonna like read through some questions, call in some random people, talk through the answers. Just let us think about what we did in the last lesson before we start on the new one. Okey-dokes. Okay. The table below gives information about 10 random U.S. residents from a recent census. There's the data that was collected. First question is, what is the population of this data set? I'm just going to call in some random people to answer. Jack, we'll start with you.
Can you ask the question again?
Yeah, what is the population of this data set?
Is it like 10 people?
So it's not, the population isn't a number. It's like, what are we sampling from?
The states and married and non-married people. Right?
So it's going to be U.S. residents is the population. Because what this is a random sample of 10 U.S. residents. And then we're collecting data about those residents. The population that you're studying, though, are U.S. residents. B, what variables are being measured? Identify each as either qualitative or quantitative. Katie.
Members of the family, age, gender.
Okay. As you're listing those, can you tell me qualitative or quantitative?
Members, quantitative. Age, quantitative. Gender, qualitative.
Good.
And then marital status, qualitative.
Good. And there's 3 others still, right? Total income, travel time, and state.
So total income, quantitative, travel time, quantitative, and then state qualitative.
Correct. Everybody feel okay there? Quantitative number, qualitative, just word, basically. That was your question. Okay. So describe in a sentence the individual in the first row. Maggie.
A 61-year-old married female from Kentucky with 2 kids.
Family members, anyways.
And income of $21,000.
Great. Yeah. Good enough, right? Just basically describing what you read. Good. All right. Based on the given data, what inferences could you make about the general U.S. population in regard to their gender and marital status? Ethan, you want to give me a crack at that?
That the average amount of family members is about 4.
So it's asking, we asked about gender and marital status was our inference.
Males are less likely to get married.
Okay. Why did he say that? If we look at the list, all of the females are listed as married except for the one that says separated. half of the married, or half of the men listed said they were never married, so that's fair. Okay. Is that a good inference? Probably not. Why not?
10 out of like billions of people.
Well, there's hundreds of millions, anyways, in the U.S. Our population's what, probably 350 or so? Not even? Yeah. Anyway, 10 out of 350 million is probably not a very representative sample size. Specifically, if you looked at just the marital status column, you'd say most U.S. residents feel like they should be married. That's a bunch of bogus. Why?
Because there's so many kids.
Because there's lots of kids, right? You're not going to be married most of the time until you're 18 at the very earliest. And even then, like the marriage rates at 18 and 18 to like 25 are still astronomically low. At least historically low, let's say that. Right? So, again, underrepresentation or something. Right, here's a scenario. In May of 2010, the Los Angeles City Council voted to ban most travel and contracts with the state of Arizona to protest Arizona's new immigration enforcement law. The Los Angeles Times conducted an online poll that asked whether the city council was right to pass a boycott of Arizona. The results show that 96% of the 41,000 plus people in the sample said no. First question, what type of sample did the Times use in this poll? Jackson, you want to give us a go there? The type of sampling they did in this poll. So that's not one of the types of sampling. Maggie, you got it?
Voluntary stuff?
Yeah, it's a voluntary response because it was set up as an online poll, so you had to decide yourself to go in and take the poll, right? You could choose whether to participate or not. That's good. Explain how this sampling method could lead to bias in the poll results. Marin, you want to give us a shot at that?
Yeah, like the people who are thought like volunteering to to do the survey, like it might be because they feel more passionate about whatever they're asking.
Yeah, that's perfect. Yeah, exactly right. So the people that most likely to respond voluntarily are the ones that have strong opinions one way or another on the topic. All right, last series of questions. So they're all about the same scenario. It says a school librarian wants to know the average number of pages in all the books in the library. The library has 20,000 books arranged by type, fiction, biography, history, so on 400 shelves that each hold 50 books. You want to select a random sample of 500 books. So first question is to explain how to select a simple random sample of 500 books. Brody, can you give us a go on how to do that?
So there's take an even amount from each shelf.
Would not be simple random. Okay? So anytime anybody asks for a simple random sample, Ethan, we'll use a random number generator at some point, but first thing you'd want to do is you index every single book. Give it a number from 1 to 20,000. Then use your random number generator to select 500 of those numbers randomly. Those would be the books you choose. Regardless of, you would not pay attention to type or location, what shelf it's on. All you're doing is randomly, you assign every book a number and randomly pull 500 of those numbers. And you could say, you drew those numbers out of a hat. If you had a big, giant hat, you could do that too. It's a big hat. Yeah, but you know, maybe you got a big head. It happens, right? Part B says explain how to select a stratified random sample of 500 books. Justify your choice of strata. Why might a librarian want to choose a stratified random sample instead of a simple random sample? And what are the disadvantages to doing a stratified random sample versus a simple random sample? Brooke.
So would you divide them into like your like categories like fiction, biographies, that?
It's the obvious choice for strata is to divide by type. Very good.
And then you pick out of those like vectors.
And then you randomly pick randomly from each strata. Yep. Why might the librarian like to do that method?
Because you have a more diverse thing, and there's simple random sample you could have like 400 fiction and 10 biography, that so you'd have a more diverse range.
Okay. That can be true. Think about logistically doing this though. What advantage is there for the person who actually has to pull these books?
20,000 books.
What's that?
You don't have to label 20,000 books, you just take a prototype.
And of the types, where do you think those would be located in the library?
Like sections,
Nearby each other, right?
Yeah.
So basically it means that instead of like walking back and forth across the library pulling these random books, I just go to a section and I pull random books from that section. And then go to the next section, pull random. So it's way less walking for me as the librarian.
Yeah.
That probably takes me, like half a day as opposed to maybe a week of walking back and forth trying to find these specific books. Out of 20,000, much harder sort of job. Disadvantage to doing so. Well, this would be less time consuming than the simple. The simples would be way more time consuming. Kirsch?
Because it technically wouldn't be fully graded.
Okay. What could happen?
She like pulls out more books from one section to another.
Well, that could certainly happen with a simple random sample. But here's the question for you. The sections of books at the library, the same amount of books in every section?
No.
No. So what if there's only like 50 books in the map section, and you pull 10 of those out, and you go to the 5,000 book fiction section and pull 5 of those out, or 10 of those out, right? Like, you can over-represent or under-represent pretty easily if you're not careful on how you're choosing your randoms from the strata. Typically, if we just say stratified random sample, we're taking the same from each strata. So you're often going to either over or underrepresent one of those strata if you're not also like, normalizing it for the amount of stuff that strata represents. Okay, part D says explain how to select a cluster sample of 500 books. Justify your choice of clusters. Why might the librarian want to choose a cluster sample instead of using a simple random sample? Are there disadvantages to using a cluster sample instead of a simple random sample? Ellie, you want to give us a go on this one?
For A.
D. What will our clusters want to be here?
It's like people are like the same.
Well, we're talking about books in a library, right?
So like of books from like the same genre or something.
Well, that would be more strata. Would be the type. Clusters are usually based on geography. So read the layout of the library here.
So like take clusters of like books in the same section in the library?
So specifically the shelves.
Yeah, the shelf.
Probably, yeah. So your clusters would be your 400 shelves. What's the advantage of doing it that way for the librarian, the person that has to pull all those books?
It's just like the most convenient.
It's really a lot less walking, right? It's pretty easy to not get lost as to what you've done so far, because you're basically taking like 1 or 2 books from each shelf, right? What's the disadvantage?
you don't have like a wide variety, it's all in the same area, so.
Well, there's only 400 shelves. You're getting like at least one book from every shelf. Now think about actually, you've been to a library. Everyone's been to a library before? So the types of books, are they all on the same shelf? No, could they run across multiple shelves?
Yeah.
Could you have 2 or 3 types on the same shelf? Would that mean it's possible that you miss a type of book entirely by picking like some books from this type and some books from that type, but the type in the middle you just missed that span 2 different shelves? That's one of the things I would think is a real disadvantage, is that it's very easy to underrepresent, some of these smaller book types. Thomasino?
So how exactly would you just word the first part? Would it just be like one book per shelf?
So it'd be like, you do like 500 divided by 400.
Okay.
So I think you get like 1.25.
Books per shelf.
Right.
Okay.
So like you're, every 4 shelves you're taking 5 books out. So like 1 book out for 3 and then take 2 out of the next one. So it'd be something like that. It doesn't have to be like hyper specific to that level, but like just kind of talking through how you do this. Notice on these questions that we did, none of these required a calculation, right? This is all using vocab, explaining how to do something, or identifying what something was. You will have test questions and quiz questions that sound like this, that are like asking you to just apply vocabulary, basically. Now let's go through section 2. So in section 1, we talked about the process of gathering data. In section 2, we're going to talk mainly about displaying that data, whether it be in a table or a graph. What are the different kinds of graphs? What are the features of them? What can we do with them? What are the different types of tables? What are the features of them? What do we do with them? Can we go back and forth from graph to table to graph to raw data to etc.? So it's about just like how we're processing and displaying our data, right? Everybody's good? Suppose there's going to be a lot of calculation here. Not so much, right? Again, it's going to be mostly like the vocabulary. What are the different types of these things? What do they mean? What are their features? How do I build this out of raw data or out of a table or out of a, etc. Okay? Okay. So, first thing we're going to talk about is displaying discrete variables. And the first example we'll look at is displaying a discrete qualitative variable. Remember, all qualitative variables are discrete because something can be orange or it can be red, but it can't be like 1.5 orange. Like that doesn't make any sense. Everybody's okay? So right here, what we have is the format of radio stations and how many radio stations meet each format. So if I look at the first table, we've counted 13,838 radio stations in total. Like 1,556 of them are adult contemporary, 1,196 of them are adult standards, and so on and so forth. That is a frequency table where it has the category and then the count for that category as our 2 columns. The table on the right is a relative frequency table. So again, what you're given there is the category title and then the percentage of the total for that category. So if I look at adult contemporary, I got 11.2% How did I get the 11.2%? I took 1,556 and divided it by 13,338 and multiplied by 100 rounded to 3 sig figs. If I add up all the percentages in a relative frequency table, what number should I get? 100. What did I get here? 99.9. What happened to that last 10%? Rounding errors, right? So if I rounded down a bunch of times, I could have lost up to 0.1% just via rounding. That's nothing to cry about. It's fine. That can happen. So again, the parts of our data table, we have the variable names listed, the values for that variable, so the format variables, or the possible format values are adult contemporary, adult standards, yada, yada, yada. And then in a frequency table, you contain your quantities are the counts. And in a relative frequency table, the quantities are the percentages of the total. Everybody feel okay? So if I want to display that data, oftentimes I would choose to use a graph to display that. If I have a frequency table, oftentimes a convenient way to display that information is with a bar graph. So notice the bar graph has the values for the variable along the x-axis, and it has the count up along the y-axis, and I'm just building my bars up to represent the counts. Everybody feel okay about building a bar graph? For a relative frequency table, oftentimes we choose to use a pie chart. Again, if it's out of 100%, the slices of the pie are just like that percent of the circle. Relatively straightforward. Again, I need a little bit of a key there to label what slice is what, but that's the general idea. Is everybody okay with that? Again, the pie slices should be proportional to the percentages involved. No big deal, right? Let's talk about some common errors that students will make when drawing their graphs. So, bar graphs, you want to make sure that the widths of your bars are similar enough that, like, if you look at them, you can't tell the difference between the widths of the bars. You don't want to have like one bar that's like this wide and another bar that's like this wide and have them both be the same height, because one bar looks enormous and one bar looks tiny. It's like, oh my God, this thing has so much more than that other thing. And it's like, well, you just have to look at the height, and they're both the same height, so they should be the same size, but it just doesn't make sense. Another common bad practice that you might see frequently, especially in like magazines and like periodicals like that. Whose family still gets like a magazine to the house? Yeah, like a couple of us, right? So I got magazines when I was a kid, but like I remember Time magazine would love to do this. They'd have their bar graph, but instead of a bar, they'd have like apples stacked up or something, right? They turn into like a pictograph. That's bad practice. You don't want to actually do that. Just use a freaking bar, you know? It's okay. It's not an art contest. It's about displaying the data accurately. Everybody's okay? Mostly because it makes it hard then to track over, like, where does the end of this apple end? I'm trying to track this over to a Y value. You know, this is like 3 1/4 apples. I don't understand. Like, what am I looking at here? Oh, that really meant 3.75 million people or something? Like, why are we putting an apple here? And I wonder why they're going out of business, the magazines. It has nothing to do with their bad graphs. It's advertising. Anyway, the two important things are like make sure you're paying attention to the scales, the bar widths, and then stay away from those pictographs. A way to represent data that includes two variables is with something called a two-way table. So you'll have a row variable and a column variable. So you could have like your row variable might be, like gender, and your column variable might be like a GPA range, where you're looking at, like the difference between academic performance in boys and girls or something. So here's an example of a two-way table. So our column variable is the chance of getting rich. The values there are almost no chance, some chance, 50-50 chance, good chance, almost certain. And our row variable is male and female. So if I look at this number 96, what does this number 96 mean?
Females that have no.
Yeah, it's the females that have almost no chance of getting rich. Okay? How many total females did we have in this survey? 2,367. How many people have a 50-50 chance of getting rich? 1,416. Everybody okay with how to read the two-way table?
Yeah.
So we can read across to get totals on the rows. You read down to get totals for the columns. An individual square is like how many people meet both attribute or have both attributes. Okay, everybody happy? Notice that the total row and column are not values, right? So your values for your variables are male and female. Total is not a value for your variable. Same thing with the almost no chance, some chance, 50-50, good chance, almost certain. Total is not a variable or value for the variable. Now, oftentimes, if you're surveying discrete data and you're building out a two-way table, you might want to group that data together. So if I'm looking at, tardies and academic performance, I probably don't want to list in my data table every single possible GPA. That's insane. Or every possible tardy outcome, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, like crazy, that stinks. I might want to give just a range of values and group my individual datas into those ranges. So I might say like 0 to 3 tardies, and then 4 to 6, and then go like that. And my GPAs, I'm going to say like less than 3, 3 to 3.5, 3.5 to 4, 4 plus, something like that, right? Where I'm grouping my data together. In general, the way to do this grouping, you find your highest and lowest values. You arrange your data into groups of equal ranges, not so that they have the same number of stuff in the group, but so that the range of values is the same size. So for example, if I go from 10 to 15, my next group should go from 15 to 20 and contain just 5 things, right? What's the catch? What's the bad part about doing the way I just said it? If I go 10 to 15 and then 15 to 20. Where's 15 go? Which group does 15 belong in? Ugh. So we got to make sure we're being really specific about the grouping. What's the best way to do that? Use an inequality. So I can do like 10 less than or equal to x less than 15. 15 less than or equal to x less than 20. And then it's crystal clear where the 15 belongs. It belongs with 15 to 20, if I write it that way. So once you've made your groups, then you just count up how many people are in each group. Again, should be of equal width. And you want to be careful to make sure it's clear where the boundary values go. So let's look at a data set here. We've recorded, we had 20 students in class and had everybody record the number of tardies they had in that class over the course of the first semester. So here's the results. So the biggest or the smallest value on this list is 0. The biggest value is 10. So I know I need to cover at least those values. So I did 0 to 2, 3 to 5, 6 to 8, 9 to 11. Notice that 0 and 10 are contained inside of those ranges. The number of possibilities in the range from 0 to 2, you have 0, 1, or 2. From 3 to 5, you could have 3, 4, or 5. 6 to 8, you could have 6, 7, or 8, and so on and so forth. Each of them contains 3 possible outcomes. So they all have the same width or the same range. Everybody see that? And then we just count up. So if I look at from 0 to 2, I see 1, 2, 3, 4 zeros. I see 1, 2 ones and 1, 2 twos. So that's 8. And I could do the same thing then for each of the different groupings. Notice I have different amounts of stuff in each group. Totally fine. Everybody good? Okay. Well, what if I wanted a relative frequency from that? I just take 8 and divide it by the total, so 20, and that becomes my relative frequency for the first row, and I continue to do the same thing there on to get the relative frequencies. Everybody's okay with how I mathed that? Pretty tough. I had to do a percentage, Mr. Kulik. Learned how to do that in elementary school math. I know, guys, but like, it does get harder, and like, there's enough other stuff going on that at least the math part can be easy for me. There's like a million names. If I want to do this also with continuous data, I can basically do the same idea as we did with discrete data. So again, highest and lowest, arrange them into different ranges. Make sure that your range or your groups are the same width or the same size. Not same size, same width. Have the same range of values. And then we count them up. And sometimes the relative frequency is helpful. So let's look at a new situation. Suppose you recorded the heights of plants, and they range from 2.8 centimeters to 28.6 centimeters. Maybe I decided to group them from 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and 25 to 30. Notice I did this using inequalities, so it's crystal clear where those boundary values belong. So 0 belongs in the first group, 5 belongs in the second, 10 belongs in the third, and so on and so forth. And then I counted up my plants. I didn't give you the raw data for this, I just showed you like how to build the table, right? If you feel like there's something missing, well, I didn't give you the raw data because, like, give me a break. You don't have to count these things every single time. Like, it's just tedious. It's beyond the scope of what we need to do. Everybody's okay? Good with how I got the relative frequencies? The other way we can do this is using a discrete boundary rather than using an inequality. I like this less, but it's still doable. So suppose we recorded the weights of players at a soccer game. So I said, okay, my category or my groupings are going to be 61 to 65 kilograms, 66 to 70, 71 to 75, and so on and so forth. What seems like the problem here? Where do I put the person that weighs 65.2 kilograms? They go in the first grouping because I round 65.2 to 65. Where would someone go that weighs 65.7 kilograms? In the second group. So that would be rows, though, not columns, right? Rows are left and right, columns are up and down. Everybody's okay? What about 65.5? What's your rule for rounding? It would go in the second column. All right, row. Now you got me doing it. Everybody's okay? So really, in a discrete situation, or if I have continuous data that I'm using a discrete grouping, you got to remember about the rounding rule, right? The other thing we have to be careful about is looking at the inequalities when we're looking at our boundaries. What's the difference between these two groupings? The first group contains 0, but not 5. The second grouping contains 5, but not 0. So they are different. You have to pay attention to the inequalities at the ends. That matters. Again, just pointing out the details here. Everybody's cool? Okay. So what we've done here is we've talked about taking individual data and turning it into group data by building these groups and counting how many of our individuals fit into every group, right? When we do that, unless you're the one that's actually doing the counting, the individual data is lost, right? If you're reading somebody's report and all they have is the group data, we've lost some individual level detail, right? We don't know how many tardies did those 7 people actually have from 0 to 2? Did they all have 0? Were there some 1s in there? Were they all 2s? You lose that a little bit, right? As a result, you lose the ability to do a lot of numerical statistic. Can you count? Can you find the true mean if you do not have the individual data? No, because you can't add up all the values and divide by the total, right? So if all you have is the grouped data, we're going to have to do some approximating to do a statistic like that. So one way we do that is with something called a mid-interval value. So that's the value that's in the middle of the data range for the grouping. And we'll use that as a proxy for the value of every individual in that grouping. So if I look at this data table, what is the mid-interval value from 0 to 5? What number is halfway in between 0 and 5? 2.5. How about between 5 and 10?
7.5.
7.5, and you get the idea, so on and so forth, right? Those are my mid-interval values. So if I wanted to compute the mean, no, we're doing this again. No, never mind. It's fine. We'll do it later. What if I have this one? What's my mid-interval value for the grouping 61 to 65? 63 is correct. How'd you get that?
Just add 2 by.
Yeah, not quite though. So here's the thing. What is the actual endpoint for the range 61 to 65? What are the actual endpoints? It's 60.5 to 65.5. Because remember, weight is continuous. So you got to be careful about that. You take those and add them up and divide by 2. You get the 63. If you did the others the other way, you know, you just got to be careful on that, right? Or you look at it and be like 61, 62, 63, 64, 65. If that's the middle number, that's fine. But if you're talking about adding and subtracting, like, be a little bit careful there. So the mid-interval value, again, it's a way to like recover an approximation of the individual data. Right? Now it's not the actual individual data, no one's saying that. It's just the best you can do if all you have is a grouped table. So for example, if I wanted to, go back here. If I wanted to calculate the mean, and all I had was this grouped data table, I would calculate the mid-interval value for my weights. So 63, 68, 73, 78, 83, 88. And I would do 63 times 8, because there's 8 people, there's 8 63s in my data set. Plus 68 times 15, because there's 15 68s in my data set. Plus 73 times 21, because there's 21 in my data set. Do that all the way down and then divide by the total, 66. And that'll give me an approximation for my mean. Very important. This is a question that will be on a test or quiz at some point. Is probably be the most missed type of question because everybody forgets to multiply by the frequencies and then divide by this. Oftentimes I'll see just those numbers added up and divide by 6 and it's wrong. Okay? Remember what the mid-interval value is doing. It's giving you it's trying to recover the individual data. So you're saying we had 8 63s and 15 68s and 21 73s, and you're taking the average of all those numbers, right? So just make sure that you really are careful and think about what it is this is doing, what is this representing, and it's easy, but boy, it's also pretty easy to like just blow right past that, kind of like, yeah, I got it, Mr. Kulik, and you don't got it. Or you forget by the time it rolls around. Okay. Okay. So let's talk about some graphs now. We've talked about tables, right? We'll come back and talk about some more tables here later in relation to graphs. But let's talk about some other graphs. One is a histogram. This will probably be the most common type of graph that we would make in a class like this. What is a histogram? It's essentially a bar graph where the x-axis is a range of data, or a range of like a grouping, and the bars have to touch. So your x-axis could be like 0 to 5, 5 to 10, 10 to 15, 15 to 20, and then your bars are touching each other unless there's a range that has 0 things in it, and then you have like an empty space. Go ahead, Evan. So again, most common mistake when students draw a histogram is their bars don't touch. When we circle back in second semester and talk about doing a Riemann sum, you're going to see why the histogram is supposed to look the way it does, because we're using a histogram very much the same way we'd use like a Riemann sum, but that's like connecting the very beginning of the course with the very end of the course, so it's hard to remember that this even happened. All right, let's take a look at some data. And we're going to build a histogram from this to show you what this looks like. So what this is the percent of residents from each state who were born outside of the US. So notice there's 50 total, because there are how many states? 50. So there's 20 states where the less than 5% of residents were born outside the US. 13 states where it was between 5 and 10, et cetera, et cetera, et cetera, right? So my x-axis on my histogram will be 0 to 5. That'll be a bar. 5 to 10, that'll be a bar. 10 to 15, that'll be a bar. The y-axis will just be counts, like how many states. Everybody's good with how I set the x and y-axis here? And now I'll just build my bars. Notice that my bars are touching, right? The first bar starts at 0, ends at 5. The next bar starts at 5 and ends at 10. So those first 2 bars touch. Everybody's good? If I don't see them touching, I'm going to mark it down. Notice what else did we do with the axes? Notice they're both labeled. The x and y axis is labeled 10 watts, right? A well-drawn graph should be labeled. The x and y axis should be labeled. And ideally, the chart should be titled. This doesn't have a title, but it would just be like percent of residents from each state who were born outside the US would be a great title for this graph. Keep on going. Common mistakes about histograms, things to watch out for. Confusing histograms and bar graphs. The x-axis for a histogram has to be grouped data. It can't be like red or orange or purple. Like you can't just list a value and make a histogram out of that. It's a bar graph. You're using, sometimes kids or students will screw up the x and y axis and they'll put like the counts or the relative frequencies on the x-axis. It's not where that goes. The x is always the variable. The y is always the count or the percentage. If you're comparing 2 distributions that have different numbers of things in them, you should be using relative frequencies as opposed to counts. So if I'm comparing boys and girls and their GPAs, if I survey 10 boys and 100 girls and I'm like, oh look, 5 times as many girls have a 4.0 as boys, it's like, well, but you picked 5 times as many girls than you did boys. Like a percentage basis there makes so much more sense, right? That's what that last bullet point is saying. And then just because the graph looks nice doesn't mean it's necessarily like a meaningful display. It's not an art contest. Although neatness counts, it's not the defining factor of a well-done graph, even if it's pretty. You know, if you didn't do a good job of putting it together, it doesn't really say a whole lot. The next type of graph we'll talk about is a dot plot. This is like the simplest type of graph you'll make. You use this for discrete data. So basically all you have is a number line with the values underneath it and a dot above each number every time an individual with that value is counted. So again, you draw a horizontal line, label it with the variable name, scale the axis, and then put a dot above the location for each data value. So here's a data set of soccer goals scored by the 2012 U.S. women's soccer team. So my minimum value there is 0, and the maximum looks like 14. Holy smokes, who are they playing? The nation of the blind? So my dot plot axis would scale from 0 to 14. I would just go up by ones. So like above the 0, I would have 1 dot, because there's one game where we scored 0 goals. Above the 1, I would have 1, 2, 3, 4 dots, because it looks like there's 4 games where I scored 1 goal, and so on and so forth. Easiest graph you'll ever have to make, right? So literally just putting dots each time you use it. What's the hardest part about this? Making sure you count the numbers only one time, right? Everybody's got to get counted and only counted one time. My hint is to cross them out after you draw the dot. Just put a slash to the number so you don't end up counting it twice, or forget to count something. Everybody's good? Okay. So let's talk about, after you've made this graph, what we want to do is we want to be able to look at it to say something about the population that we sampled from in general. So what we're doing is we're going to look for an overall pattern or a departure from that pattern. So when I talk about pattern, there's 3 attributes that we would talk about: the shape of the graph, the center of the graph, and the spread of the graph. Okay? Yes? Sure. And we'll talk about in a moment what each of these shape, center, and spread mean a little bit more detail. When we talk about departures, we're talking about outliers. Values that seem very far from the rest of our data. Again, as we move further along, we'll talk about how to numerically identify outliers. So the way we remember this is SOCS, S-O-C-S. So shape, outlier, center, spread is the acronym that is commonly used to describe those 4 attributes. So shape. In shape, what we're looking for is one of 3 answers. The data can be symmetric, where you have about the same amount of stuff on one side as the other. If you draw a center line through the middle, you have the same amount of stuff. Or the range of values should be the same on either side. I should say the range of values. If it's skewed right, then the range on one side is way longer than the other. So if I look from center to last value, that range is longer than the left. That's called skewed right. And skewed left is just the reverse. If the left side range is longer than the right side. So let's look at some pictures here. If I look at that data set, symmetric, skewed right, or skewed left? Well, the center looks like it's right there around 6 or so, correct? So the one side goes from 6 to 2, the other goes from 6 to 12. That's about the same, isn't it? That, I would say, is symmetric. Close enough. For a skew, you're really going to see it. If I look at this one, what do you think this looks like? Looks like skewed right. Notice the center looks like it's around 1 or 2. The right-hand side of that goes way further to the right. Everybody see that? So we'd say that's skewed right. How about this guy? That that looks skewed left, right? The center there looks like it's around 85 or 90, right? And the left-hand side of that graph looks longer than the right-hand side. So we say skewed left. Jack, I have a get out of jail free card for you to grab. That's you, Jackie K. So if I want to compare two distributions, oftentimes the comparison that we make would be using shape, outlier, center, spread. So you say, oh, this one distribution is symmetric and the other is skewed left. One distribution has a center of 5 and the other center looks like it's 10. You know, something like that. Sure. So for centers, what we're talking about is usually the median, and you can just kind of count each data point in. You know, like start one from each end and just kind of count in until you find the middle value or values. Is everybody okay there? The spread is just the distance between the smallest and lowest. Right? That's easy to identify, the smallest point and the biggest point. Just the difference between them is the spread. Or is the range, and that's a proxy for spread, excuse me. The difference between the biggest and lowest is a range, but that's a good description of spread for right now. And outliers are like, you just kind of know it when you see it. For right now, we'll talk about how to do it numerically later. Another type of graph is a stem and leaf plot, or sometimes just called a stem plot. So the idea here, you're going to have a vertical column of numbers. That's the stem. That would indicate, like, you know, maybe the tens digit or the hundreds digit or something. And then the leaf is the final digit. So the leaves are always just numbers between 0 and 9. You can't have double-digit numbers as leaves. So we start by just writing out all of our stems from smallest to largest in a vertical column. Draw a vertical line down the right side of that column. And then we write our leaves on the right side of the stem. And then we organize our leaves in increasing order out from the stem, from smallest to largest. And then we provide a key. Most common mistake students make when they draw their stem plot is they forget to give a key. Very easy to forget. You're like, I got it all done, and then I forgot to say what it is. You know. So let's say this is our data set, and we're going to make a stem plot out of that. If I look at this data set, the smallest number, it looks like it's 13, and the biggest number is 57, right? So I need 10s, 20s, 30s, 40s, and 50s. So my stem should go from 1 to 5. So in the ones, in the tens place, I have 13, if I scroll across, I have a 19, a 13, a 13, a 13, and a 15. So I'll write down the numbers 9, 3, 3, 3, 5. And then I'll do that the same thing for all my 20s, my 30s, and my 40s, and my 50s. And once I've added my leaves, I'll sort them smallest to big. Notice there's no commas here. Everybody see that? No commas in a stem and leaf plot. Am I done right now? What'd I forget, Katie? You shook your head. I forgot to write a key. So here, the directions say this data was the responses of 20 female AP statistics students on how many shoes do you have. So 4/9 represents a female student who reported having 49 pairs of shoes. Girls, what is it with the shoes? You can only wear one pair at a time. What do you need 49 of them for? Good Lord, that's almost a different pair every week of the year. You know, if you're a gentleman, I think I have, including my running shoes, I think I have 5. Dress shoe, 2 casual shoe, running shoe, and then lawn mowing shoe. Right? Like, that's it. That's all I need. There's variations on stem plots. So two variations you can do. You can have a split stem plot. So if you have a lot of data, like one of your stems might have like 25 leaves on it, well, that stinks. That's a big old long list. So what you can do is you can split your stem. So you might include like 2 1s and 2 10s, 2 20s, 2 30s, 2 40s, 2 50s, and then have the leaves 0 through 5 on one, and then, or 0 through 4 on one, and 5 through 9 on the next one. Or you might have 2 sets of data that are measuring the same thing. Like if I did a shoe survey for girls and a shoe survey for boys, maybe I'll do a back-to-back stem plot where I'll do 2 vertical lines and put the boys' leaves on one side and the girls' leaves on the other. That's a back-to-back. Or you can do both, right? Like you can split the data and make it back-to-back, which is what we're going to do in this example. So here we have some boy shoe data and girl shoe data. Again, here if I look at my minimum value now across both data sets, that's now a 5. So I'm going to have a 0 for the 1 spot, and then a 10s, 20s, 30s, 40s, 50s. So I picked up an extra number in my stem, and if I'm going to split it, I'll then have 2 0 spots, 2 1 spots, 2 2 spots, 2 3 spots. So for the first stem of 0, I'm going to have any leaves that are 0 through 4. And the second stem will contain leaves 5 through 9. So I do that on one side for my dudes. And then for my chicks, we do it on the other side. And that's the gist of it, right? Like, no big deal. But you got to know what the vocab means, right? What a split stem plot means versus a back-to-back stem plot versus just a regular stem plot. Am I done with what I've done here? I need a key still, yeah. Notice this time when I wrote it, I wrote 4/9 represents a student instead of a female student because now I have boys and girls. So I just was going to be broader to include that it could be either side, right? One calculation we will do in this section is percentile ranks. So a percentile is the percent of the distribution where the observations are less than the individual. So as an example, Jenny earned a score of 86 on her test. How did she perform relative to the rest of the class? So we're going to give that performance as a percentile rank. Here's the 86 right here, the boldface 6. I'm going to count the number of scores less than 86 from the class. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1. So 21 total. And then I beat 21 people. And then I have myself and then 3 scores more, so there's 25 total people. So Jenny's percentile rank would be 21 out of 25, or 84%, or the 84th percentile. You guys all took a PSAT a year or 2 ago. Remember how your scores came back? What do they come back as? Percentiles. So if you got a 79 in math, it means you scored better than 79% of all other, 10th graders that took the test or whatever. Everybody's okay? So another type of graph that we often use to calculate percentiles or to approximate percentiles is something called a cumulative relative frequency graph. So here's a grouped data for the first 44 presidents and the age they were when they were inaugurated. So we had 2 between 40 and 44. I think Obama and Kennedy were those 2. 7 from 45 to 49. 13 from 50 to 54, 12 from 55 to 59, etc. I don't think this has been updated. How do I know that right away? I think Trump was 70-something in this most recent inauguration, and there's no category for him. So I think this is, it's the first 44. Trump is what, 47?
Yeah.
He got 2, he gets 2 spots though, him and Grover Cleveland. So if I want a relative frequency, I just make those into percentages. If I want to get a cumulative frequency, so this is, to get the 9, I'm taking 2 plus 7. To get the 22, I'm doing 2 plus 7 plus 13. It's like a running total, right? Just down your table. Very easy to do, but you got to know what it means. Cumulative just means total so far. And if I want a cumulative relative frequency, I can take my cumulative frequencies and divide by 44, or if I have the relative frequencies, I can just add up the percentages, right? 20.5 is 4.5 times 15.9. Why did it? If I add those, I got 20.4. Why is it 20.5 here? Rounding, right? This was probably 4.51, and this could have been 15.94. When I add them together, it rounded up to 20.5. So, like, if something feels like it didn't add up the right way, it's probably just rounding. It's okay. No big deal. If you have the frequencies, use the frequencies to get the cumulative relative frequency rather than the percentages. But if all you have is percentages, that's all you can do, right? Notice when you add up, or the last row in your cumulative relative frequency has to be 100%, right? Okay. So what I can do then is I can create a cumulative relative frequency graph. So this is just 0, and then 4.5. So at 45, and then 50 is 20.5, et cetera, et cetera, et cetera. So if I wanted to, I can use this graph now to estimate the percentile for presidents that were born. What percent of presidents were 53 or younger, or less than 53 at inauguration? So I just find like 53, I track up and I track over, and the percentile's like 35 or something, right? I'm just going to estimate. If I had grid lines, I could be more precise, but I don't care. Or I could say, at what age are like 80% of presidents this age or younger at inauguration? So I just do 80%, I track over, and then I track down, and it's like, 62 or something. Again, if I have grid lines, I can be more precise. Is everybody okay with that? It's just like reading a graph. But once I built this, I can use this to estimate percentiles for things that I didn't actually measure, right? That's the point. Yes. So you can do this as a cumulative relative frequency, where my y-axis is percentages. Ugh. Or I can do this as a cumulative frequency graph, where my y-axis now is count. So remember, there's 44 total presidents, so the top of my graph is 44. And it's the same picture, right? Just the only difference is the axis is labeled differently. So you can do it the same kind of way. if I wanted to find like the 25th percentile on this, well, my total is 44. 25% of 44 is 11. So I find 11, I track over and track down, and it's like 51-ish or something. Is everybody okay? So I can still do all the same things. I just might have to do a little bit of extra arithmetic to know like what y value corresponds to the percentage. But like, what did he do? Again, not hard, but you gotta like know what you're looking at. All right. Okay. So when we talk about the C in center, the most common center measurement is the median. So that's the exact middle point of the data. So if you have an odd number of data set or odd number of observations, you just order them smallest to largest, and the middle number is the median. If you have an even number of observations, you order smallest to largest, and the average of the two numbers in the middle is the median. Everybody's okay with that? Remember this from like middle school math, mean, median, and mode, hopefully. Median's the middle number. So if I have a data set like this, it's like, okay, find the median of this. Well, it's not hard, it's just really tedious to do this by hand, right? So I have to start by writing all the numbers in a row, smallest to biggest. Oftentimes doing a stem plot is an easy way to do that. And then I just count now to the middle. So like 1 from the end. I'm just counting. And these are the middle two then, at 20 and 25. Is everybody okay with how I counted in? And you just like, I would just like put a slash through the number as you get one, count one from each side. Everybody's okay? So I do that, and it's the median then is 22.5. We'll also show you how to do the calculator ask the calculator to do this. In the end of the day, almost everything we do in this class is going to be done with the calculator, especially this like you have to sort it and count. Like, forget that mess. I'm going to show you how to do it on the calculator, and the calculator will just do it all for you. You just have to know how to ask it nicely. So you can type in the data set as is, and it'll just spit out the median for you. And I'll show you how to also type in a data set, and it'll sort it for you from smallest to biggest, or biggest to smallest if you want it that way. All right, next thing we're going to talk about are quartiles. How many quartiles do you think there are? That's a trick question. There's 5. I know. There's Q0, Q1, Q2, Q3, and Q4. So Q0 is the minimum in your data set, the minimum value. Q4 is the maximum value. Q2 is the median. Q1 is the median from Q0 to Q2. And Q3 is the median from Q2 to Q4. Does that sound like a pain in the butt to do by hand? Sure is. Guess what the calculator can do for you? With one command, I can get the mean and the median and the quartiles all in one shot. So that's nice. Anyways, again, remember these quartiles are also percentiles. Like the 0th percentile is Q0. The 25th percentile is Q1. The 50th percentile is the median, or Q2. The 75th percentile is Q3. The 100th percentile is Q4, even though technically the 100th percentile doesn't exist. Because you can never have higher than all the data, all the measurements, because you are one of the measurements. So your score can never be better than all the scores, because you can't be better than yourself. Ruh-roh, Raggy. But that's the idea. Everybody's good? So the cumulative relative frequency graph, if I want the minimum, that's the 0th percentile, or also Q0. That was 40 years old. If I want the first quartile, that's 25%. So I find like 25% like here, trace over, trace down, about 51. If I want the median, that's 50%. Trace over, trace down, like 56-ish. Third quartile is 75. Trace over, trace down, maybe 61-ish. And then the 100, Q4 is the 100th percentile, so like 70 or 69 or something, I think. Okay, 70, we said. Everybody cool? Really easy to get the quartiles from a cumulative relative frequency graph, right? We're just reading it over, you know, like tracing over. If I had a relative frequency graph or a cumulative frequency graph rather than a cumulative relative frequency graph, what do? I just take the total count, the 44, and find 0% of that, 25% of that, 50% of that, 75% of that, and 100% of that. So 0, 11, 22, 33, 44, and just trace those values over and gets me the same thing, right? And I'm done. Thank goodness, Mr. Kulik, that was a lot today. Good news, the next 2 days, we're going to do some in-class activity, so like you don't have to sit here and listen to another boring PowerPoint slide. You get to actually collect some data and do some stuff with it. That'll all be done in class is the hope. We'll also, over the next 2 days, talk about the first step in your IA. So you guys are gonna start thinking about topics and writing some topic submissions. We'll have some time to do that as well over these next 2 class periods, and we'll talk about the process that you guys will use to do that, and we'll get that going. Sound good?
Yes.
Okay. If you happen to be absent on the next 2 days, I will record the class data set for you to use, and I'll put that in the OneNote if you happen to need it. So just a heads up, if you happen to be absent, or if you just lose your paper and like, I don't have the data anymore, I'll have it on the OneNote. I feel like